Hi guys, this video is just a refresher of calculating the seismic coefficient factor CDT value, and we will come across different some of the annotations that are quite strange and unfamiliarized, such as CT and CHT and so forth and so on. So in this video, we will try to investigate what are they and to understand them, what effects they have to the building we are designing. So we have step one, calculating the building period T1. We can we can do it by two methods. We can use empirical methods, that is according to Eurocode, and we can also use it for radius method. But the difference is that empirical method is straightforward. You just need to figure out what your lateral system is. For example, if you have a concrete shear wall, for your lateral system, you just plug a KT value to be 0.05, and you got your building height HN, and it gives you building period T1. That is straightforward. And for radius method, it goes a little bit deeper into calculating your deformation and the inertia forces, which is durable. You can use a small angle theory to get your DI, which is a deformation. And of course, you got your equivalent static force, which is Fi values, inertial forces, and your building weight as well. And by substituting all these values, you get your building period. So this radius method is fully capturing your building weight, your deformation, and your inertial force. So when I'm heading to a develop a design stage, I will use radius method to be accurate, because this is determining my seismic side amplification factor CHT. This is the design spectrum graph from 1170, and by looking at it, so your side coefficient factor CT, just be aware of that. That is different from your amplification factor CHT. So the side coefficient factor, it is a combination of your amplification, your location, which city is it, and your annual recurrence, what is the probability of the earthquake, 1 in 500 years or 1 in 25 years, and your near fault factor, how close is your side to the fault. If it's larger than 20 kilometers, your building is not getting any penalties, but it's smaller than 20 kilometers, then meaning very close to the fault, and you get penalized for that. Usually end up with a high value is like 1 point something rather than 1. So the CHT factor is the amplification. If you got a building period, for example, 0.4 seconds, your sort type is C, and you can figure that out by looking at a graph here. You get your amplification factor is about 2.4. That means your seismic design action is going to be amplified by 2.4. Sorry. So to understand this, you've got different soil types, A and B, all the way to E. The A and B stands for usually very hard rocks, okay? And the E is going, the way it's going up, the soil type gets weaker, and the soil type E stands for very soft soil. To understand this, I would like to go a little bit further. So in 1985, the Mexico City earthquake, okay? So the Mexico City is founded on an ancient lake soil. It's very, very soft soil. Here, down there are many buildings on the top. It's between two mountains down the valley here. It's very bad soil. It's probably a creek or river running through thousands of years. And then founded the city, and I found the buildings on top of it. And one day the earthquake hits. Imagine this is my earthquake epicenter, and it goes through my site, and when it hits the rock, okay, this is sort type A, gets the rock, because the rock are stiff, they are hard and stiff, they are able to absorb the energy that is coming from the earthquake, right? But however, when it keeps travel through, because the energy needs to dissipate and get out of this zone here. So once it hits the soft soil, and because it's so soft, does not have much stiffness compared to the rocks, so the energy gets you know amplified. They need to get out of here. So it's creating this extra excitations on the building. So the building wax crazily, back and forth. Huge energy gets dissipated throughout this crust. So this explains why under the same period of the building, for example here 2.5 seconds, my building if my building was founded on a rock, I get very low amplification. If my building was founded on soil type A, very soft soil, you see my amplification is high compared to what it was on a rock. So this explains when you get your geotechnical report, read it, what's the soil type, and you can plug into, okay, what is my amplification factor for CHT? And you do a combination of those factors and eventually get your CT value, which is site coefficient. That is the determinant factor for what site you're having and what effects to your uh, design building. And next, we move on to ductility and structural performance factor FP. So as we know that we have to determine what level of damage we are expecting for my building, right? If it were like I want to design my building, I don't want any damage, right? I have to design my building to be elastic. So I am using my ductility of 1 for uh, fully elastic. So it's coming, so the building is coming, when earthquake hits, energy hits it, forces here, my ability to recover is 100%. I have no damage. It's coming back, and coming down. So my building performs really well. So my structural performance here, this you can call it or and uh, understood it as a expectation of the building. So that one means, okay, I'm designing my building as fully elastic, so I'm expecting 100% of my building is performing well and no damage at all. And by comparison, if I had my building to be nominal ductility 1.25, I'm expecting what? I'm expecting a little bit of damage to my building. I'm going to say, okay, my building is about 92.5% overall. It's good. It's only got 7.5% of my building is damaged. You can, I think it's better to understand this way, in terms of SP factor. So you can imagine if you have a ductility of 2 or 5 or even 6, your SP factor gets what? Lower. Because you are expecting your building to be damaged more if you are having a higher ductility, right? Makes sense. Okay, move on to the scaling factor. There's another factor gets into way to the final design your seismic coefficient. It's mainly to do a few things: your ductility, what ductility you're using, and what's the building period. And if you were using like ductility 1, you're having your scaling factor basically as 1. So your structure is not gaining much bonus, I would say, for designing your structure. If you're having your ductility of, say, higher, limited ductility, 1.5 or something like that, and you would end up something more than 1. That is more than 1. So that means if you have something more than 1, and your seismic coefficient is getting reduced because you're using higher ductility. Your higher ductility, you are expecting your structure to perform uh, to be damaged some at some extent. So you are factoring up your KMU factor, so you're getting your lower seismic coefficient, and then that it comes to your base shear is coming lower. So that's kind of a trade-off in terms of a seismic coefficient. Um, so when we do design, we got to be careful in step 4, calculating this KMU here. Right, so this is the refresher of calculating the seismic coefficient. Yeah, just have a look through. If any questions, just yeah, make a comment below. Yeah, thanks for watching.